It is my honor and privilege to acknowledge that the Games Institute and the University of Waterloo is located on the traditional lands of the Haudenosaunee, Anishinaabe, and the neutral peoples. The land that was taken without consent from the First Nations that I just mentioned, and then it was sort of kind of returned to them in the Untitled Chapter treaty that promised 6 miles or 10 kilometers on either side of the Grand River as the land of which the First Nations would have custody of and would be the guardians of. That obviously didn't work because we now here work on this land. I also live very close to campus, so that's the land where I also live. And those of you who are outside of our region, I will let you do your territorial acknowledgement based on where you are located. We do the territorial acknowledgements to not only remember about the history, but look to the future and how we can, in our day-to-day jobs and day-to-day activities, acknowledge the enduring presence and philosophical beliefs and cultural significance of the First Nations around here. And as we are working in the realm of games and technology, as a community, we try to uplift the voices that have been minimalized and silenced for generations, and the Games Institute has done quite a bit. I hope you will all agree on bringing those voices up to our attention, and I hope that will continue. So with that, welcome everyone to a very exciting talk that we have today. I'm going to ask those of you who still have your microphones on to mute them for a moment, just so that we don't have feedback. We have two speakers today, John Edison Muñoz Cardona and Dr. John Edison Muñoz Cardona, I should say. Sorry, John. And Dr. Alan Pope, who are going to be doing sort of like a coffee chat conversation almost, I think, John, you noted to me. So it will be less than a formal lecture, but a very interesting conversation between two scientists. And so thank you very much to all of you for joining us. As you, those of you who have been here before know that we have some housekeeping things to talk about. Just a very brief, for those of you who have not been, and I know that we have some people from outside of the Games Institute community. The Games Institute is one of 8 university-level research centers and institutes at the University of Waterloo. And the slide that you see right now is a very brief overview of what the Games Institute does and what we stand for. And what we hope to achieve. And so if you have any more questions about the Institute, I will be very happy to stay behind and chat to you about that if you are new to our community. And for those of you who are here and from our membership, just a refresher for you, I hope, since I bore you with this particular slide every term at the town hall. So. And finally, Sophie was kind enough to post this into the chat. These are just housekeeping reminders for today. We are recording only for internal purposes for those of our members who couldn't be here today, and for John and Alan to take a look at the presentation and what they would like to change or augment before their presentation proper at GDC later this month. Keep your cameras on if you feel comfortable doing so, so that the speakers actually know that there is an audience and they're not just talking to each other. But do keep your microphones muted just so that we can avoid any unnecessary background noise. Participate actively, and John will be taking the honor and privilege of moderating questions as they arise. So you can either raise your hand in an electronic sense or put your question in the chat, and John will try to weave that into the conversation. And just a reminder, this is online, so we don't get all of the normal human interaction cues that we get, so just be kind and considerate and take into consideration potential connectivity issues that some people may experience. And with that, I will stop sharing my really boring things. And I will invite John to please introduce himself and his research, or reintroduce it to us, and then introduce Dr. Alan Pope for us. And with that, John, over to you. John, your microphone is muted. Yes.
Cool. Thanks. Sounds good. Thank you, Agata. Thank you all for coming here. All the feedback that you can give us is going to be well received. Been trying to polish this presentation for GTC. And yeah, I just going to briefly start. I think we have this 60 minutes presentation, so we will try to keep it in 45, 50 minutes plus for the questions. So again, this is going to be more like a conversatory, like more like a coffee chat. And yeah, try to see how it goes. Welcome everyone, and thank you for being here. The title of this talk today is how NASA has translated aerospace research into biofeedback game experiences. My name is John Muñoz. I am a research scientist and a game designer working at the University of Waterloo. With me, I have Dr. Alan Pope, which is a distinguished NASA researcher associate. He's a biofeedback expert and technologist. He has invented many different systems that can be connected and work with biofeedback technologies, and he's probably one of the pioneers in this field that is called physiological computing. Welcome, Dr. Pope.
Thank you, John.
So in this talk, we're going to be basically describing a lot of the work that Alan has been doing with a lot of the people from NASA Langley. This is in Virginia, and you know, different inventions and different systems that they have been pioneered from the last 2 to 3 decades. And has the you can see in the slide is basically a whole range of different applications, from flight decks to physiologically adapted games. So we will try to focus on the games aspect and try to deconstruct some of the technological elements and the game design aspects that are involved into it. So the goals of this talk are in a sense related to try to better understand, you know, what do we call physiological computing, and what is this specific mechanism called biofeedback loop. We try to bring some of the examples and discuss the different systems that have been designed by NASA modulation team. We will try to explore some of these biofeedback game mechanics while we, you know, bring examples and while we try to deconstruct them. We will later show some of the more recent tools that we have been designing, and you know, some people can use it. They are already there available, and we will try to also refer to a specific future directions as we see pertinent. So, Dr. Pope, the field of physiological computing. I mean, we have many different definitions for this, but I always like to hear, you know, what do we call, or how do we reach to this point in which we call, you know, biofeedback technologies? We call wearable computing. We talk about signals, physiological phenomenon. You know, we put together this specific term. You know, can you tell to the audience, like, you know, what is physiological computing?
Well, I suppose there are formal definitions for it, but my idea is that anytime you're attaching sensors to someone and having that interact with digital technology, a computing system, a computer, then that's the basis of physiological computing. Some of the things we'll show are physiological computing in open loop applications. I think you had a slide on here on user experience research. That's open loop kinds of things. And my entry into it was in aviation safety research, starting way back when. I worked for NASA for about 40 years, and I've been retired for about 5 years. And so the safety research that we did was look at concepts like hazardous states of awareness, which you can find in the literature, and adaptive automation. And hazardous states of awareness research was done in an open loop fashion, just by monitoring what someone is doing and interpreting their mental state, try to determine what kind of conditions led to good attention, good alertness, and what kinds of conditions in the flight deck mitigated against that. And also adaptive automation, using physiological measures to adjust the level of automation or aspects of automation to adjust it to the person's state in the moment. So that's kind of our approach to our applications of physiological computing. And the game systems that I'm going to talk about are spin-offs from that core research. As you can imagine, developing video game technology isn't a NASA priority. There are a few other things that take precedence over that. But these are spin-offs from the core research that I sort of briefly mentioned.
I think that's what makes also this talk interesting, because you cannot you don't realize that whole NASA is kind of like involved with any type of development and creation of gaming systems until you get to know your work. So in physiological computing, for those that are not very familiar with, we try to use a lot of the different signals from the body, ranging from electroencephalography, electrocardiography, electromyography, electrodermal activity, and we try to sense the body in order to better understand people when they are interacting with systems. Of course, when we talk about games, we got this concept of the game loop, in which there's a player interacting with a gaming system, and then the gaming is providing feedback constantly, and this is pretty much a closed loop system. I think a lot of the things that we will show here today are related to how to complement, augment the conventional game loop by using physiological signals. How can we do that is what is as being defined as a biocybernetic loop. But you can also find those in the literature. You can also find things like effective loop or biofeedback loop. Mm-hmm. And in a sense, what we try to do here is to sense what the player is feeling and the physiological reactions that they are having, and we try to create an augmentation and a modulation of the game response based on that. Biocybernetic loop. What is who came up with that concept?
Well, I'm not sure about that. I know that biocybernetic loop was coined by Stephen Fairclough in Liverpool, but he claims to have derived that from my work. I don't know. And the term biocybernetic adaptation is one we've also introduced. And a simple way to think about that concept, biocybernetic adaptation, is it's what you get when you replace a display that's driven by a client's physiological signal, say in biofeedback, with a task that the person is interacting with in other ways. And that task is simultaneously being influenced by the user's physiological signals. And that's the basic paradigm for the modulated game systems that we'll talk about. I came to this through biofeedback therapy services, which I provided for some time back in the 80s as a clinical psychologist outside and prior to my work with NASA. And so this is kind of a development built on that kind of background, biofeedback background.
Mm. Yeah, and you mentioned something that's also very interesting from your background. You have this clinical background, but you also did electrical engineering.
Yeah, my master's degree is in electrical engineering, and my clinical degree is my doctorate. And some people find that strange, but I don't. It's a logical combination to me, but it led me into this kind of closed loop application.
And I think it goes very well with the different systems that you were creating, because certainly they require that combination of skill set. So I remember what I just when I started checking all this systems and all the things that you guys were doing back in the 80s. This was one of the first examples that So the automation that you were planning in the slide deck, and this is some of the pictures that I've seen from the settings that you had in the lab.
Yeah, the graphic on the left there is a graphic that was developed back in '87. The idea of some kind of entity monitoring the physiological signals of the flight crew, and that at the time that was our image of open loop research, just monitoring and measuring and trying to determine what kind of physiological or psychophysiological state the crew were in. And we moved from that into spin-offs that were closed loop feedback systems. And the picture on the right is my colleague Chad Stevens and myself working with a small mock-up. This is not one of the large simulators that we worked in later. And out of that, we developed what we're going to be talking about today.
Yeah, this is a short video of all the settings and the pilot that you were testing, and how was the scenario, the sensors as well that you were using to basically monitor that those psychophysiological states of people. Or you were trying to find things like workload, stress, engagement levels, isn't it?
Exactly, engagement and what we coined hazardous states of awareness, which are things like preoccupation and distraction and absorption and those kinds of things. And this is the technology as it was back then, and that's my younger brother. No, that's me. Back in the day, so this is the kind of advanced concept flight simulator that's been replaced since then by even more advanced flight simulators. And this is the EEG monitoring that we were doing at the time.
Pretty cool technology. That was what, 80 something, 90?
This was in the early 90s when we were doing that thing. Yeah.
Very interesting. One of the things that I noticed also, and that is some of the things that we would like to bring in this talk is, these are like lab conditions, and these are pretty much very controlled conditions to do this type of research. But outside, and especially when we work with kids, we always try to be kind of like practical, try to be pragmatical in all the tools and systems or the tools that we try to implement and integrate into our research. And I think this is a very interesting example. This is the so-called engagement index, which was basically some of the things that you were using there to quantify the level of engagement of people while using electroencephalography. I think this is a pretty cool example of what are the things, how do you translate the knowledge that you're getting from very much controlled scenarios towards something that others can use?
Yeah. Well, I came to this measure kind of backwards. My interest was, if you had a signal that meant something, what would you do with it? I was interested in what you would do with the signal. And of course, eventually came to the idea of games and adaptive automation and that kind of thing. But what I needed was some sort of simple real-time measure. And when I looked into the literature, that kind of ratio that you see there was something that we created just from what we found in the literature about what beta activity and alpha activity and theta activity represented. So we were looking for just a straightforward index, and to my surprise, that's been used by a lot of people since then. We intended it as a placeholder, and I suppose it is a placeholder for a measure like that, because the way you would do that today was you would use machine learning to derive some kind of model of the individual and not just use a simple ratio. But the ratio has worked, to my surprise, amazingly well.
Mm-hmm. And still does. I also use it for some of my research. I think it's a nice way to complement all of the metrics that you can get from EEG. Mm-hmm. Mm-hmm. So from that to those companies and initiatives that you were spinning off out of your research. So how was that, transition coming from a, very much control lab scenario and trying to, use similar concepts in game systems?
Yeah, well, it occurred to me that the simulators we were working in were basically video games for grown-ups, or video games for professional pilots, I guess. And so we thought, well, maybe we can apply some of this technology in a closed-loop way with video games. And since we didn't have the ability to access the software of these video game systems, we implemented them with off-the-shelf games, but without requiring access to the game software. And the way we did that is an approach that I think you have a term for, John, that I appreciate, is we MacGyvered it. We used what we had available and made do with that. So these images and the following video are early feedback modulated PlayStation games. And in this particular case, the MacGyvering was the controller buttons were modified to produce a stream of pulses instead of just a constant switch closure. And the rate of that stream of pulses was driven by brainwave signals. And that meant that the speed of on-screen objects like cars were proportional to the strength of the brainwave signals. And one way to think about this is that conventional video games provide an incentive to improve hand-eye coordination. And what we're trying to do here is to provide an incentive to get better at producing a target brainwave pattern.
Mm-hmm. Yeah, and once the player was kind of like producing or getting into that target, what type of modulations were you doing in the game?
We were changing the speed of a handheld controller, the speed of the object that you're driving. We also modified, or at least disrupted, the steering control. And the whole idea, though, is to disrupt or augment the controller input itself, external from the console, this off-the-shelf console, in a way that provides an incentive for a person to produce a particular brainwave. And so we were changing those kinds of things. And later on, we got into looking at the Wii, which we'll talk about a little bit later. But the video that you're showing now was a study that was done at Eastern Virginia Medical School with kids with ADHD, encouraging them to produce the brainwaves that accompany attention. And so what we did was use the kind of thing that I just described as a technology. And this is one of the kids in the study interacting with it. And this is my colleague, Oliver Paulson, who's a clinical psychologist who actually conducted the study. And the finding in this, where they were playing a video game, where the speed of the controller, speed of the object in the game through the controller was changed by their brainwave activity. The result of this was that both the video game the biofeedback modulated video game technology and a conventional neurofeedback system produced the same kind of outcome in terms of subjective report and measures of attention that were taken afterward. The only difference was that the kids were more interested in coming to the video game biofeedback treatment than they were the just displays that were presented in the conventional neurofeedback system.
And I certainly, at that time when I started learning more and more about the systems, I also became more and more curious to actually try myself. And at that time, it was back in the country Colombia, and I was very much into games and using also physiological sensors. And he is also an example of a similar concept. I mean, I kind of like got inspired with some of the gaming system that you were doing, combining neurofeedback therapies. I just did it in, using kind of like more recent technology. So we took a wearable system that you were using also at that time, using Unity as a game engine, and at that time we were also working with ADHD, children with ADHD, and kind of like trying to co-design some of these games. And you can see this is a more kind of like recent game that was also created to help children with ADHD to train their attention while playing games. And for now on, also going to try to show some examples beyond the work that you have been doing at NASA, and in a way to show how I was getting some of these concepts and kind of like try to see how to apply them using more recent technology.
Yeah, the way you did it is the way that we would like to have done it. We would like to have been able to do that, but we weren't able to develop the software ourselves. And that's why we went the way we did and did that kind of hacking of the controllers. So this is the way that we had in mind, and you did it.
I think, yeah, some of the examples, come back to hacking some of these consoles. And, at that time, as you mentioned, you were not, you didn't have probably the tools or access to the tools that probably we have today, like, the very sophisticated game engines like Unity or Unreal. So I like the things that you were doing with the Wii, and some of the combinations that you were doing between the brainwaves and motion sensors.
Mm-hmm. Well, this is a picture of the Wii video game that we developed, and being demonstrated by an age inappropriate player. The modulation method here, the MacGyvering that we did here, involves disturbing the Wii remote cursor by replacing the sensor bar with an array of LEDs, infrared LEDs, that causes the cursor to move around the point where you're pointing with the Wiimote in a frustrating way, again disrupting your play of the game. And the cursor movement becomes less and less. It calms down and becomes stable as you approach the target brainwave signal. So this is another incentivization scheme that we came up with, and using it without having to go into the software of the game.
Yeah, and I think that concept is pretty unique in a way that it's modifying the direct control input of the game. So instead of being directly controlled by the motion sensor that we have in this case, the Wii controller, and you kind of like modulate or modify in real time the stability of that cursor. So it really, I can easily see how this will easily become a very frustrating experience.
Yeah, and as you can see in the video, there's a light bar on the right that indicates how well you're doing. Down in the red is not good, and when it gets up in the green, you might be able to detect that the cursor becomes stable. But when it drops down, there it is. It's in the green now, and now the player then it's back down in the red, and it's jumping around. So and the perf board that you see just below the screen there is where the infrared LEDs are located in an array that takes the place of the sensor bar.
Mm-hmm. Yeah, pretty cool concept in terms of modulating the different game mechanics.
Yeah.
So, and I feel very empathetic when you mention, or when we talk about MacGyvering and hacking all of these sensors, because even with like more modern technology, and we put together this framework to actually get the physiological signals from wearable sensors like smartwatches or headbands, bracelets, and even though they were coming with some SDKs for us to kind of like extract and try to get the signal, still it was a lot of MacGyvering time that we had when trying to connect and stream the data and get that data into, in this case, Unity. So in a way that can be used to, produce biofeedback game experiences. So in this specific framework, it's called VCODR. We also had a lot of trouble in trying to pair the sensors, which were most of them Bluetooth, with a mobile device, and then streaming then in a way that we can capture in the game engine. So the modulation will come right after, but building an ecosystem of tools that people will be able to use to prototype these type of biofeedback experiences is something that I've been also doing and passionate about. But I think at that time when you were hacking all those tools, you were just working with the sensors that you had available at that time, which probably were not a lot.
That's true. Off-the-shelf kinds of things, headsets that the companies didn't allow you to know how they derive the measures they derive, which is kind of frustrating. So you just use the measures that they present. And this particular slide is the first VR slide that we've got so far, right? So this is when we're getting into VR here.
Yeah, that was back in 2016. Interestingly, I remember you were also exploring, beyond the virtuality, beyond the 2D screen or even the head-mounted display. How can you modulate physical objects by using, inner regulation or physiological regulation? And this is, I think, an interesting example of how you can do that through a mechanism that you created for training golf players.
All right. We're back in physical reality here, and the thinking that was on my mind back then was, everything we're doing up to now is in pixels. What can we do in the real world? What can we do in a physical realization of these kinds of things? So we took a off-the-shelf putting mat, practice mat, and once again hacked it and made a lot of changes to it so that you could disrupt the play until someone produced a particular physiological signal. So the idea here is that the green itself undulates back and forth when the physiological signal is not on target, and I think is there an image of the hole. The hole opens up and closes depending on how close they are to the target physiological pattern. Yeah, I think you can see that. You can't buy those, by the way, that iris is a shame. And this is Catherine Hull Kirk, who was trying this out at the LPGA tournament in Williamsburg. So the idea was to try to take things off the screen and put them in the real world and see if we can modulate things in that way. And the invention patent that describes this includes a lot of other things like basketball and tennis in kind of outlandish ways.
I think one of the key concepts over here, something that you mentioned before, is a specific target state. A dedicated or a very particular psychological state that you were targeting in order to make those modulations. And I think that concept was also very insightful when I was doing my PhD in Portugal. So I also decided to kind of extend a little bit more the games. This was a game created for training older adults, and that concept of targeting, in this case, specific heart rate levels in older adults, which we believe are beneficial to help them with the cardiovascular health. And the concept of trying to modulate the game based on that specific target. So in a way, in this case, it's the classical phone game in which the ball speed is modulated by the presence or not of this specific targeted state called target heart rate. So if the older adults were, in this case, in that specific range, the ball was changing and increasing or decreasing the difficulty, which at the end will allow and persuade people to move more or less, depending on their target heart rate. So again, expanding or extending these type of physiologically modulated system towards more physical reality, sort of like that.
Yeah, yeah. And I might mention that the target that we were shooting for with the putting practice mat was a state that Debbie Cruz at Arizona State University, who's very much into golf training with brainwave activity, had defined previously. So we simply built on that and used that kind of state, which is basically a state of mindlessness, alpha kind of state where you're not thinking, which is not what you want to do when you're putting. You don't want to be thinking about other things.
Mm. Yeah, I noticed you were using EEG for the paddle.
Yeah, we use that for what you see in the picture there is actually EMG, because that was easier to implement in a demonstration. But we used an off-the-shelf brainwave headset for the next iteration of that technology.
Cool. That's one of the challenges that we have is, okay, how do we choose the correct signal? How do we certainly combine the signals to make a concept of a biofeedback game? And I think this is also an interesting example of how you guys managed to combine not only different signals but conventional game mechanics with biofeedback modulation concepts to certainly again hack or work around some of the games that already exist, so you don't need to deal with all the graphics and creation of the virtual environment, but then you modulate some elements of the game difficulty based on those.
Let's see, which slide is up now? Oh yeah. Oh, this is this is something using the emotive headset, and this was actually what we intended to get to initially, but we had to do all that hacking kind of thing. A game that we could have access to the software, and so a couple of our interns, Chris Jones and Tyler Pavowski, managed to use this particular game, which is what is it?
Fallout
New Vegas. Yeah, Fallout New Vegas. And get into it, because there are tools in which you can actually get into the game and change the capabilities of the weapons and the abilities of the players. And that's what was done here. And I think this is the one that Chris developed and showed that you could control your ability to aim and fire, and he shows the effectiveness of firing when your brainwave activity was not indicating frustration and it was indicating excitement. So those two measures from the emotive headset were used to drive this kind of mechanic in the game. And I think in a few seconds he also demonstrated that combined with the physiological modulation of the game capabilities, you could add in the Connect movement sensing, and even combined with the Wii remote sensing. I think there's a little window that pops up with Chris here in a moment.
Yeah, I think at the end of the video, it shows also that specific type of combination between the motion sensing controllers and some of the physiological sensors that are there as well.
Yeah.
So,
old square.
Yeah. Very seems like a very complex scenario when you have multiple signals plus all the games kind of running, and then you do certainly adaptations in real time. And indeed, when you work with this type of systems, what you do is you do multiple adaptations. So it's not like you just change one variable, but the main point of this is keep constantly adapting the game based on what you are recording or measuring using your physiological sensors.
Right. Mm-hmm.
One of the concepts that I also saw and called my attention was, this idea of doing this biofeedback gaming in a multiplayer fashion. So in multiplayer games, in which we certainly required more some settings for both sensors to communicate to the game and to the specific game engine, and then what is the type of game mechanics that you can create when you have more than one person playing with this type of biofeedback game mechanics. And this concept of physical operator and a physiological operator was certainly interesting, and I think you described it pretty well in a patent.
Yeah, well, this came out of a problem that we were having, because in some of these things, movement interferes with the pickup of the physiological signal with the sensors, and so it sort of occurred to me, well, what we could do there is have one person be the physiological operator, physiological player, and the other be the physical player, so that the physiological operator is not moving around and interfering with our signals. And that's the problem that this came out of. And what that does is it enables someone who is differently abled to play along with a physically able player as a teammate.
Yeah, I think that I kind of like use part of that concept also to assist in the creation of experience. I was working more like a biofeedback technologies here in this specific experiencing, where we were trying also to combine those signals. In this case, we have two different operators or two different players with two different sensors. One was a respiration band, and the other one was the wearable BCI. And what we did here was kind of like allowing them to get to use their own powers or the powers of the other player only if you were able to regulate yourself. So your partner's power is activated by your own regulation, and that was a way that we were trying to push people towards a collaborative gameplay while keeping this adaptation using physiological signals.
Yeah, you can see how that would lend itself to cooperative gameplay between the two kinds of players, or it could be some tension if they didn't cooperate with one another.
Yeah, and I think that aspect of multiplayer brings another level of different game mechanics that can be implemented there, and especially now that everyone is talking about VR and social scenarios and how to connect multiple people. Definitely, that's a very promising direction for this type of research.
Yeah.
I like this example, this next example, in which you were using this very old head-mounted displays back in the 90s, and somehow you were also exploring what you can do in terms of visualization of the physiological signals using head-mounted displays.
Well, let's avoid the word old and call this legacy. I'm a little sensitive about that, but this was as you say, a vintage VR system. But when you think about this is not really modulation here. This is simply a different kind of biofeedback display. Instead of a graph or a bar or something changing, going up and down or something, this is actually the representation, as we imagine it, of the blood vessels under the skin. And their effect on the skin would be temperature or pulse picked up by a light sensor. Then we just show what the blood vessels are probably doing under the skin when these measurements, temperature and pulse, are being sensed at the skin. And this came out of the concept of synthetic vision, where pilots can see the ground in a synthetic vision system. They're not actually seeing what's there, but they're seeing a representation based on where they are in location. And I just translated that by analogy into this kind of beneath the skin, where you can't see unless you've got something sensing that can display kind of a cartoon of what's going on. We call this our Fisher-Price display of blood vessels.
Yeah. I'm curious to see, like, you try yourself? You try with this specific prototype, and what's the feeling of immersion?
Yeah, as you can see there, the person is raising their hand and lowering their hand, and you can see the changes that take place there, and you really you can, after a while, get the feeling that you're kind of inside that part of your body, and just seeing the blood vessels there. And it was tried out, not really studied, but tried out over at the Eastern Virginia Medical School Diabetes Institute, because the idea was that if you can encourage a person's blood vessels to expand when they're having peripheral neuropathy, then the blood flow increases to the periphery and kind of offsets some of the effects of that.
Yeah. Part of our collaboration started when we were trying to expand on some of these concepts you were bringing, related to game mechanics and the use of virtual reality headsets. And I remember what we had was basically I did an internship for the National Institute of Aerospace in the States. That's when we formally met back in 2000, I think, at the beginning. And there was a licensing program, which I think is still up, isn't it, for companies in the States to be able to use, many of the different inventions and kind of like create products out of it.
That's true. The inventions that we've come up with, most of them have been patented, and those patents are available for licensing, and some of them have been licensed. It's the usual patent licensing process that NASA has as an institution.
Mm-hmm. Well, what we did at that time, there was this company that called JNF Alliances in Hampton, Virginia, that licensed some of your patents. And my feeling was like, they were having like a good sense of the potential of this technology, but they probably didn't know exactly how to use it. And I think that's why we got this opportunity to basically prototype some of the biofeedback virtual reality applications that we will see. And one of those ideas were, how can we use this as a conflict de-escalation programming, how we can use this physiological signals to better quantify police officers and then to better sense their reactions when they are holding a weapon.
Mm-hmm. Yeah, and the company was struggling in finding how and what to do with the patents that they had licensed, and when you came on board, you were able to help them realize the implementation of these things.
Yeah, and that was nicely showcased by the NASA Spin-Off magazine, where we were kind of like moving from all those inventions to more, towards more modern virtual reality technologies. And I personally had a lot of fun working with not only the company, but also your team, Beth Langley, and also the police officers that were coming, and they were also so excited about wearing the sensors and going into the simulator that we put together. We had we used some commercially available sensors like the chest strap, polar chest strap, and also the Muñoz BCI. And what we tried to do there was kind of like trying to quantify the level of engagement of being in the zone, as you previously described, and kind of modifying some things in the simulator, in this case, the speed of the target or the hardness of the target, and the quantity of targets that they were having. So this is, these variables are modulated by using their own physiological regulation.
Yeah, and you were able to implement this entire project in how many months? 3?
it was around 3 months that we were kind of like running with, all this implementation. And I think that it encourages to keep pushing forward to, how can we prototype this in a way that, it doesn't take months, even years to get to something that is like a playable prototype. And we pushed this a little bit forward, and we came together into a game jam as well that was remotely at that time. That was run at the Games Institute at the University of Waterloo, and we were trying to see, okay, what can we do in the game jam? I think it was 2 days of the game jam, and how can we prototype something around these? And we came out with something that is mostly for training lucid dreamers in meditation, which is supposed to be beneficial to foster these specific skills. And, this is kind of skill that can be trained. So we came out with this concept of, using biocybernetic loops to modulate some content using virtual reality in this case. So we use the Muñoz BCI to collect some of the neurological or neurophysiological signals. In this case, we were using the frequency bands to modulate some variables inside the simulator. So we got 2 different scenarios on this. We're using different applications to collect the signals and to get them into the game engine. In this case, we were using Unity. So you can see here that we developed some tools to get those signals into Unity and be able to get more focus on what you can do once you have the signals, and also once you detect the psychological state, what you can do with that information inside a virtual environment. So in this case, we did 2 different scenarios in which if the person or the player is able to produce the targeted signals, in this case, a modulation of beta waves related to the meditation state, then we will create these random animals or random trees and kind of like populate the virtual environment, recreating that metaphor of, the randomness of the dreams sometimes. The second scenario, we were more pursuing the face your fears scenario, when we have like a big spider that is about to attack you, and then you need to stay calm and stay somehow relaxed in order to defeat the spider. So this is again a prototype that we did in a weekend using some of the tools and concepts that we have previously described here. And I think that was a way of showing, like, it's possible to prototype these biofeedback games in just about like a weekend, or doing it in a more interactive way. As a summary of the talk, you have here some of the biofeedback game mechanics that we mentioned previously. For instance, the control input, where you can, some of the ideas you can use this as a game mechanic in your game is like, the special weaponry challenges, kind of like modify the player's features, provide power-ups, or just to, bring a cool interface into your game. That's, the example of the modify Wii games. You can also use this as a difficulty adjuster. So again, to level up or to work more like the rubber band regarding the enemy. So as close as you are of the targeted state, then you will have enemies behaving in different manners based on those the proximity of your physiological regulation with that target state. Engagement, you can work into creating more engaging experiences by modifying the things like the environmental variables. For instance, you can change the weather conditions, you can change the light or even the sound based on how well the player is modulating or regulating their own physiological signals. I think these are is a summary. It's a good summary of the different ways that you can use biofeedback in mechanics in modern games. Any comment here, Dr. Bull?
No, I think this is a good summary. It goes all the way from the kind of hacking that we did to something that is the way you would want to do it these days.
Yeah, and part of trying to prototype all of this game mechanics is it also comes along with the creation of tools. So we also created and polished a tool that is built in Unity, in which we can allow game designers and game developers to not be worried about the acquisition and the processing of some of these signals, but be more focused on the concept that they would like to prototype. So we can collect the signals already inside Unity. We created also a console in which you can create adaptive rules using, there's blocks, and then you have tools like the Fourier transform to get like frequency variables that are more descriptive about psychological states like engagement or like stress. And then, you can connect this to the games that are created in the game engine in a way that you can modify the variables based on those physiological reactions. So you can see here, you can create the rules in real time, and then you can, change and prototype them based on any game created in those game engines. So yeah, lately we have been basically creating many different tools and try to make them available for people, especially the game design and game development community. So in a way that they don't need to MacGyver. A lot of the things that we were doing in the past with the sensors, but they can use commercially available sensors, and they can bring those inside the game engines, and again, stay very much focused on the types of games that they would like to create using this technology, rather than dealing with streaming the information and capturing that information inside. This is, also an interesting example with the Max Planck Institute. It's called the Excitometer, and it's freely accessible in the GitHub repository if there's people interested. We also recently plan to use some of this physiologically adaptive systems and try to see what is the impact of the systems, especially using virtual reality, for people that have been socially isolated, like a lot of people that have been going through this, and especially astronauts. So we put together also a grant application for the European Space Agency, and we're looking forward to see if we can bring this technology to space. Future directions. Dr. Pope, what do you think we should, how can we invest over time if we want to create these type of experiences?
Well, I think you've got a good point there about developing these prototype biofeedback games, but I would also like to really see be made commercially available these toolboxes that don't exist yet. You've got the BLE, the Biocybernetic Loop Engine, which is kind of a model for that kind of thing, so that when designers or developers want to incorporate this modulation into games, they don't have to do it from scratch. They can rely on toolboxes that are available, like toolboxes are available for other kinds of mechanics and things in games. And also the game expansion packs that you have for other purposes in games, those could be specialized for physiological modulation, so that the player can change their favorite game in some way just by using an add-on like that.
I'm also very excited to see the new sensors coming. They're already embedded into the head-mounted displays, and I have my hands on into how to prototype virtual reality games using sensors that are already embedded into it. So looking forward for those.
Yeah, for those two that you mentioned there, right?
Yeah, I think that's being all. I'd like to thank you all for being here, and we're open to questions.
Hi, John. I have a question of my own, but there were a couple of things in the chat, so maybe you can take a look at that in the meantime. I'm not an expert in human-computer interaction or anything like it, but when you say you're hacking / modding / MacGyvering things, what's your take on intellectual property? Because game producers don't often. I mean, things have changed since the beginning of this research, and now we have Unity is open and other game engines exist. But when you're hacking or modding, devices, game consoles and things like that, there are IP issues with that, aren't there? When you're tinkering with equipment, how do you as researchers approach that?
I guess that would be directed to me as MacGyver. We haven't concerned ourselves with it, I suppose. We haven't actually tried to sell any of this, and the only thing we do is patent the idea, and someone can pick it up, and the licensee can deal with the IP issues when they want to incorporate it in their product. But I think there are a lot of folks who have modified things like the Wii controller and that kind of thing, and we really don't. When you think about the Wii thing, we really haven't changed anything that was proprietary. We just sort of worked around it. But that would be the issue for a licensee, I think.
Thanks. John, there were a couple of questions in the chat. I see Ale, who had to leave the meeting for something else, asked which kind of physiological measurements are used for the player. I think this was in one of the earlier slides.
Yeah, I think some of the tools or like some of the signals I put here, it's kind of like the most popular ones. But there's like a whole list of many different signals that you can collect. I think nowadays the limitation is not that much into the what type of signal, but the what you do with it, like how do you transform those signals into something that is usable as a game mechanic into your game. I think that's the challenge right now, and for that we try to use more like psychophysiology fundamentals, in which they mention about the relationship between physiological signals and psychological states, like engagement, like stress, like workload. So we always try to go around those principles and kind of like describe those psychological states in using different features from these physiological signals.
Okay, thanks. I'll let Ale know that was answered. Also, Leila left you a bit of a suggestions for the few slides, so I'll let you take a look at that. But I don't see there were any other comments or questions in the chat. So thanks very much. But, oh no, Michael has his hand up. Go ahead, Michael.
Hi, can you hear me okay?
Yes.
Yeah.
Okay, great. Just a quick question for you, Alan. And I guess it kind of piggybacks on this idea about intellectual property. But what's your opinion about making game content far more open? The way I see it, we have available to us incredible tools for creating very evocative content to understand how the brain works, for example, how to solve real problems, map and develop applications. And yet there's real barriers for creating that content. Have you come across any solutions or do you have any insight in terms of how we may, as scientists, collaborate with game companies to actually create a more open play space to be able to, push the future of this technology for the betterment of everyone?
I wish I could offer something, but we haven't dealt with that issue. We haven't approached. Well, actually, there have been a couple of companies look at, like Nintendo, for instance, looked at our Wii implementation, but at the time they weren't interested. So I don't have any experience in fostering that kind of openness of the technology. I will say there are a lot of people doing similar things. We weren't the only ones to MacGyver these kinds of things. One of the things that inspired us about the Wii is that someone showed that you could actually play the Wii video game without the sensor bar. You could use a couple of candles, and when you see those kinds of things, you start thinking, well, that makes a lot of things possible. You're not restricted to just what the game company offered you.
Yeah, and there's certainly there's definitely been a bit of a change in the culture from some companies as well. That will actually encourage hackathons or encourage the next generation of programmers to use their devices and push the limits of them. And of course, they're highly interested to then perhaps employ these people or help them to commercialize it for various reasons. But in the actual content space, there's this massive gap where game companies, AAA game studios have the ability to create amazing works of art that they certainly need to retain some intellectual property and rights to. But anything that can be done to sort of open up that content for other use and other use, as you said, this was not done for the purposes of alternative commercialization, but rather for advancing discovery and developing new applications. So, yeah, hopefully we'll see a push to more open, shared content in the future that might help resolve some of those issues.
Well, we're dealing with the same kind of issues with the sensing technologies. There are companies that have brainwave headsets that provide you with a measure, but don't tell you how they derive that measure. They don't give you the algorithms or anything like that. So I'm hoping that'll open up too.
Yeah, I agree. Yeah, completely.
I had, if I may, a follow-up actually to Michael. We have, and Michael, I think you had found some similar or came to similar conclusions in your work, but we have partners at UYT, another university here in Ontario, and they were looking at training of doctors, surgeons in VR. And some of the research pointed to the fact that an actual narrative included in the training tool actually affects how people respond to it, how fast they learn, and what sort of their, I don't think they were doing biofeedback in their research, but how the trainees were responding to the technology and what was involved in it. I'm wondering, Michael, I think you had similar research that pointed in that direction. And I'm wondering here if, biofeedback.
I think you've cut off, Agata. I can't hear you anymore.
Oh, 1, 2, 3.
Now you're back.
Yeah.
Okay. Michael, maybe you can speak to that a little bit more from your experience.
Yeah, well, I mean, we were interested in, sort of the motivation and the background stories that people are familiar with, of the training that they go into user experiences with, in the attempt of understanding how that information help ameliorate problems with cyber sickness, for example, in virtual reality. And what we were able to find was that if we provided people with a very enriched narrative with very clear directions in terms of what was expected of them, then there seemed to be much less uncertainty when they were performing their tasks in virtual reality. And they also reported less cyber sickness. And that effect of that enriched narrative was mostly pronounced amongst those that had very little gaming experience, actually. And so this brings up issues with respect to human-computer interaction and familiarity with the technology, that if you put these tools in the hands of somebody who's quite naive, it can be very daunting, troubling, disorienting for them to use it. But if you give them very clear guidance and really give them a purpose and an understanding of what they should be doing, and there's a great utility here in using games, then, that you can use the narrative of a game to help motivate people to perform the tasks that are required of them. And not only will it increase their performance, but can also ameliorate these problems of cyber sickness that people have found.
I think the closest thing that I'm saying is actually a game that is available on Steam, which is called Nevermind, which also is a biofeedback game that uses heart rate, and of course they have all the narrative around it's a horror video game, and they change some of the variables in the game based on your heart rate or heartbeats.
That brings. Yeah. Go ahead.
Oh no, I was just going to add to that comment that there's a lot of interest in sort of enhancing the user experience in this sort of content, right? A horror is a great one because it's so evocative, and also using biofeedback to temper the user experience too. That if the sensors were able to detect that somebody's entering too much of a state of anxiety, for example, you could maybe tone down the horror in the content until they're able to sort of advance to the next level. But that was all I was going to add, Alan.
Well, that brings to my mind an experience I had when we sort of deployed the blood flow virtual reality system, where it's portraying the blood vessels. The medical school made a video with Dr. Vinnick, who's a prominent researcher in diabetes research, working with a patient with the virtual reality system. And he did a lot of coaching, trying to describe what kind of feelings the person should experience and what kind of thoughts they should be having. And I realized at the time that how I had flipped over into my engineering mind and not my clinical mind, and I just thought you just hand it to them and let them work with it. But he knew better. He knew that you basically had to guide them through that kind of thing and explain what was going on and try to access their experience. And so I was corrected.
Thank you. It seems that stories help human beings. Funny how that works. Michael, any other questions?
No, I'm good. Just thank you very much for the great talk, and thanks, John, for putting this together.
Yeah. Thank you, John. Thank you very much, Alan, for joining us today. John, I'll be in touch about the recording, and do take a look in the chat. There's some specific comments for your presentation. So I'll let you get in touch with the people who suggested things in the chat yourself. Okay. Dr. Pope, it was lovely to meet you. Thank you very much for attending the Games Institute, albeit virtually. Perhaps in the future we will be able to welcome you on site here. And John,
thank you.
Thank you very much for putting this together, and I'm sure we'll be in touch.
Sounds good. Thank you, Laura.
Thanks. Thank you, everyone.
Yeah. Bye.
Bye.